cryptanalysis session. So the first talk is differential cryptanalysis in the fixed key model, and the talk is given by Tim Boehner.
Okay, can you hear me? Yeah. So, like Maria just said, so this talks about differential cryptanalysis in the fixed key model. So, I mean, I think the people who go to this session probably have some idea what differential cryptanalysis is, but it doesn't hurt to just quickly review that. So we have a function f, I'm going to call it, and then we'll take an input x, add some difference a to it, and we're going to see if the output pair has a certain difference b. And ideally, we want to find such a pair of differences, that's also called a differential, so that there are many inputs x, so that this kind of difference equation holds. And then the number of such x divided by 2 to the n is what we call the probability of the differential. And so the basic problem that this paper deals with is how to compute this probability. So in general, that's pretty difficult, but usually we have some structure. So the structure we have is that our function is a composition of a number of much easier functions. And what we then do is we build a sequence of intermediate differences. That's what we call a characteristic. And what you have is then that the probability of your differential is the sum of the probabilities of all the characteristics. So that's a first simplification, but it still leaves open the problem of how do we actually compute these probabilities of the characteristics. And to do that, people basically make an assumption, which is that the propagation under each of those functions fi can be assumed to be independent, which doesn't really make sense because all the intermediate values are just deterministic functions of each other. But you can make that somewhat more reasonable by saying that if you add round keys, so uniform random round keys after each of those functions, then the average probability of a characteristic can indeed be computed by just multiplying probabilities. But that gives you the average, and you actually want to know more than the average. You want to know, ideally, you would actually want to know the fixed key probability. And so to bridge this gap between the two, people have introduced this hypothesis that for any particular key, the probability is probably close to the average value, and that's this hypothesis of stochastic equivalence. And so we can actually try to check if that makes sense for some examples. So here I take a differential for 6 rounds of spec 32. And then because spec 32 has only a 32-bit block size, you can just experimentally test how many right pairs there are. And so if the hypothesis of stochastic equivalence was correct, you would expect that like near this red line, we would have some kind of peak in this histogram. So most of the keys should give a probability that's close to this. But as you can see, that's not really true. So you have lots of different peaks in there and a lot of things going on. I think the most important for practice, the most important conclusion for this is that if you were to use the average, then this would actually give incorrect conclusions in this case. Because, for example, let's say you think, okay, I take 2 to the 13 pairs, and then on average, I'd expect one right one. But actually, there are a bunch of keys for which that just wouldn't be enough. So you'd be saying that your success probability is much larger. But this is still a moderate case that can be much worse. And one thing I want to mention here is that I've been talking about this average, but actually it's not the average because the round keys are also not independent. So even if you just want the average, you can't just assume that the round keys are independent. So in order to address this problem and to kind of explain figures like the one I just showed, what we introduce in this paper is a new technique that we call quasi-differential trails. So it should really be called differential trails, but unfortunately the term is already taken. And to get there, I'm going to first introduce some sort of extension of the difference distribution table, and then from there get those trails. So, so these matrices, these quasi-differential transition matrices, The way we get them is by applying a sort of recipe. So the recipe is what I've introduced in the context of linear cryptanalysis as the geometric approach, which just like the very basic idea is that you have some combinatorial problem and you convert it into a sort of more geometric problem. So the combinatorial problem that we are interested in here is you have a set, so you're going to encrypt this set, and then you want to determine the size of the intersection with this set and some other set. And you can make this kind of more geometric by expressing this intersection size as an inner product between two vectors. I mean, two vectors or two functions, that's basically the same thing. And the vectors we consider here are the indicator functions of sets. So the indicator function of a set is just 0 everywhere, except it's 1 on the set. So that if we have that, so we were talking about these indicator functions, but we actually want to know also if you have an indicator function of a set, how does that change if I apply a function? And that's actually that there's a linear relation between this given by some matrix. So you just do a matrix vector product, and the matrix is very easy to define. It's just mapping delta x, which is 0 everywhere except it's at the value of x. So it's just a vector with a single non-zero entry to delta f of x. And so this is some matrix that gives this relation. The only thing here is we are working with pairs, not just with individual values. So we need to do the same thing basically on sets of pairs. But the idea is exactly the same. You can build some kind of matrix. And in fact, if you are familiar with tensor products, then you'll easily see that your matrix or transition matrix for pairs is just a tensor product. So now we have this transition matrix for pairs, so that's cool. And it really fully describes this propagation of sets of pairs. So theoretically, it also describes exactly the probability of differentials. But like practically speaking, that's, I mean, what we've done is completely useless. We just rewrote the problem a bit. So to actually make this into a useful theory, I'm going to introduce a change of basis. So change of basis, so the idea is just that, so let's say you have here a picture of my co-author, and then you do some linear transformation, the blue matrix, and then you get some other picture. So this linear transformation is represented by this blue matrix with respect to the blue basis, right? And you get a different matrix if you choose a different basis. And so when you look at it from the point of view of the blue basis, it's actually a pretty complicated matrix. But if you choose, for example, the red basis, then it suddenly becomes a diagonal matrix, which is much nicer to work with. So the idea here is actually, for choosing this red basis, I chose vectors such that, so this vector here, so anything parallel to that will actually be mapped to itself. And here, this one, you know, it just gets flipped, right? So that's why this is a diagonal matrix. So we're going to do the same thing now, but do this really big matrix, the transition matrix for pairs. And that means we have to choose a basis, of course. So how are we going to choose the basis? There are two sort of natural properties that you would want this basis to have. The first one is that you want to include the indicator functions of sets of pairs with a constant difference. So those are these delta A functions. And the reason for that is that this is what we use in differential cryptanalysis, right? And then you also want your basis, and this is related to the whole fixed key thing, to be, so you want everything to behave really simple when you're going to add keys. So key addition means you're adding to both halves of the pair, you're adding the same constant. So you want it to be a translation invariant basis. And there is a solution for that. So this is one possible basis. And there are also the 2 to the 2n basis functions. And I will index them by a value u and a value a, and u will be called the mask and a the difference. So you can immediately see that if you put u equal to 0, so this becomes 1, then you get the functions we wanted to include. So that's good. And if you're going to add something, so do this translation, then because this chi u, that's basically -1 to some linear function of x. So you're just going to get a constant vector that doesn't depend on x or y. So so we have the properties we wanted. That's good. And I mean, if you are like more theoretical, then you might want to, like, if you want to generalize to other groups, you might want to know this. The reason why we use this particular basis is because this guy of u is a group character. So now we have this basis, and then we can just do a change of basis on our transition matrix, and that's what this quasi-differential transition matrix is. So there's nothing more to it, but if you're a practical person, you probably want to know what the actual coordinates of the matrix look like now. So what they actually look like is, so I'm going to index the coordinates, that's the first thing I should say, by these mass difference pairs. Why? Because otherwise I have to number the basis vectors in an arbitrary way. And it seems a bit silly to do that. So what you actually have is some product of the probability of the differential, and then some term which is 2 times the probability minus 1. And if you are familiar with linear cryptanalysis, that's what we call a correlation. So here we're actually, so this is a measure, let's say, of how biased some expression is. So here we're measuring how biased some linear combination of inputs and output bits is. And we're doing that only for the values that satisfy the differential. So you could say that in a way, this quasi-differential thing is just sort of linear cryptanalysis restricted to the set of right pairs. So then we can compute this for specific S boxes. So for example, this is the rectangle S box. So you have the DDT of that. And then your quasi-differential transition matrix is a kind of zoomed in version of that. So where for every element of your DDT, you would get a whole submatrix of your quasi-differential transition matrix. And then, so the top left elements in each of those, like that, that's going to be the probability of the differential. And then if you take differences equal to 0, you get this correlation matrix. So if you're familiar with linear cryptanalysis, that's a very important object there. Now we have this matrix, and then we can try to, so I'll show now how we can go from there to trails. So the main property that we need for that is that if you have a composition of functions, then the quasi-differential transition matrix is just going to be the product, so the matrix product of a bunch of these, for these functions, so the quasi-differential matrices for those functions. And then you can just take this matrix product and write out the coordinates just as a sum, right? So you get some sum over some products. And then the terms in that sum are what we call these trails. So they are sequences of pairs of masks and differences. And so then the products here are what we call the correlation of a trail. And this is useful because the correlation of trails is usually easy to compute, because your functions fi do have some structure that makes it easy to compute these quasi-differential transition matrices. And then the interesting part is if we take masks equal to 0 for both the input and the output, so then we get on the left here, that's the probability of the differential. And then it shows that the probability of a differential is exactly equal to some sum of correlations of a number of trails. And the idea will be that we select the most important trails and work with them. Yeah, if you were to remove all the terms from this sum where the mask is non-zero, so you keep only masks which are 0, then you basically get the standard thing we do. So just summing the probability of characteristics where those probabilities are computed by multiplying. So, but this shows you actually need to take into account a bit more. So another thing that you might want to do, so that's for computing probabilities of differentials. So you often also want to directly compute the probability for a characteristic. And then you do kind of the obvious thing. So you just sum only over the masks because the differences are already fixed in your characteristic. And it's easy to see that this works. Like the differential characteristic is just a differential, but for a function where your intermediate values are also part of the output. So then if you specify the differences here, this fixes your internal differences. If you specify the masks, so that there is this general rule for how the masks propagate. It's basically the same as in linear cryptanalysis. Then because this is 0, there will be arbitrary masks before and after your forking operation, but they have to be equal. So you have to sum over all these trails. And that's why you get this result. So now we have trails. So those sequences, and then we can try to use them to actually explain some phenomena. So so first of all, so you want to find the best trails, because that's, I mean, we're going to still do an approximation where we replace this sum over a huge number of terms with just a sum over a small number. And for that, you can use some automated tools. In this paper, we used SMT modeling. And then for the small functions, you need some algorithms to compute to make the quasi-differential transition matrices. And so there are some algorithms that are, so you can compute it in about the same time as the size of your matrix. So that's pretty good. And for modular additions and bigger functions, we have a formula. And then we apply this to 3 ciphers that we chose, mostly based on how easy it is to talk about them. So rectangle, where we show the best attack that's been published, doesn't actually work, although you can fix it at least partially. Then K0, that's a hash function in the lightweight crypto competition. There were some collision attacks proposed on that, but it turns out the characteristics used in that attack just have probability 0, so you're not going to find a collision with that. And then we also looked at spec. So just briefly say a bit about spec. So first, I want to go back to this example I showed at the beginning. So here, if you do this automated analysis, or even manually, if you have a bit more time, then you'll find there are 5 trails which really have a much larger absolute correlation than the other trails. Then if you just take into account those, so there are 3 key bits, 3 linearly independent key bits. This one is just a linear combination that actually can influence this probability in a significant way. And then you could, you can just compute what possible values can that give. And so this is the red lines here, and you can see that it matches those peaks. I mean, you can also compute how many keys there would be in each of those peaks, of course. And so this gives a sort of simple model. If you want to improve, you just need to take into account more trails. Similar to that, you can explain some experiments that were recently published at SEC, I think. That's even easier, actually. That case, there you only have 2 trails. And then we also looked at some actual key recovery attacks. Yeah, basically, the conclusion there is like most of the key recovery attacks that have been published only work for like 1 in 4 keys or less, with some exceptions like spec 96, where it only works for 1 in 64 keys. The positive side to that is that for the keys for which the attack could actually work, you can do with a lot less data than what's expected. I just want to mention that it's not like I tried to find differentials where like the results would like from the literature would be wrong or anything. So I expect that if you try any attack, that it's very likely you'll find that actually there are some inconsistencies or some improvements in some cases. So just to conclude, so we've got this new thing called quasi-differential trails, which are constructed from quasi-differential transition matrices. And then we applied those in the paper to a number of attacks. So we used SMT to find that, and you can find the source code for the SMT tool we have at this link. But yeah, I think there's a lot of future work here. So one thing is that you can just take any attack and then actually try to take into account these additional trails and see if the key has a significant effect. And my expectation is that in many cases, that will be a very significant effect. There are also I think it's interesting to improve these tools because there are some actual very specific optimizations that could be done because our paper doesn't focus too much on the automated analysis. And then one last thing I want to mention is that the limitation of this method is just the same as in linear cryptanalysis. So this is a theory where you have trails, but trails don't explain everything because you can have a large number of trails which have a combined effect that's still very important. But for that, you need to go beyond just theories with what I call in this geometric framework one-dimensional trails. So you need to go further than that. Okay, that's everything.
Thank you very much, Tim. So are there any questions? There is a question in Zoom from Michael Abramson. I'm going to read it. He says, have you tried this attack on Des, since that is where differential cryptanalysis began?
So have
If you tried to apply this on Des.
So in the paper, there's an analysis of the original characteristic that's used in the attack by Biham and Shamir. So there's actually, I mean, it was known there that there is a quite significant effect of the key, which is actually, I mean, if you use, so there are actually two characteristics that are used in the final attack on DS to compensate for that kind of, and so yeah, you can explain that with just one quasi-differential trail, which is local to one round. So if you iterate many rounds, you'll get several copies of that. Yeah, I also checked then if there are, in that case, even more quasi-differential trails, but it turns out not to be the case. So that's the main effect there. So, but yeah, we looked at it.
Thanks. I have a question, maybe a bit naive one, but so in the cases where you found out that the attacks didn't work, or that a small proportion of the keys would be the ones where the attack worked, could this give us also information on the value of the keys when the attack doesn't work, for instance? Could this be exploited to recover key information?
Yes.
And have
I mean, not
looked at
much,
that,
but a bit, yeah.
Sorry?
Like a little bit of information about the key, yeah.
And you don't think it could be exploited to, I don't know, to learn more things about the key?
Yeah, I mean, so it depends because so it could like so in the like for example for these attacks on spec. So let's say you have this thing where it only works in 1/64 keys. So you find out that it doesn't work, then you know, yeah, that is not one of those. That this is you can know exactly what this class of keys looks like. But I mean, those will be internal bits of the key, so that's already less clear if you can directly use it in a key recovery or something. But yeah, you get a little bit of information. That's true.
Okay.
But yeah, it doesn't really save the attack.
Okay. Are there any more questions in the room or in Zoom? So if there are no more questions, then let's thank Tim again. Thank you very much. And the second talk of this session is Simplified Meet-in-the-Middle Modeling for Permutations, New Quantum Attacks. And the talk is given by Andres Rotendorf.
Okay, do I have a voice? Yes. Thank you for the introduction. So yeah, this is a joint work with Mark Stevens, and this is going to be about meet-in-the-middle attacks, modeling, permutations, and quantum stuff. So I have to unpack a bit here. Let's start with permutations. So cryptographic permutations, there is no key. In this presentation, there is no key at all, but we're still going to try to find attacks on that. And our goal here is to find an input X, which has some relation between the input X and the output P of X. You could say, for example, I want to search a fixed point of this permutation if there is one, and that means X equal P of X. The way to solve it with the meet-in-the-middle technique is to select two subsets of the internal states of the permutation, one that we're going to compute forwards, the forward path, and one that we're going to compute backwards, the backward path. and we're going to compute them independently. So we take all the possibilities for these forward states, all the possibilities for these backward states, we compute independently, and then there are points at which these two subsets are going to match, to meet, and we take all the possibilities, all the pairs of possibilities which are going to match in these points. And once we have something that matches, we're going to recompute everything and to try to see if our conditions are all satisfied. Of course, this works because there is this condition here, which basically closes the computational path of this permutation. Well, this is broadly the idea that we use. The application, of course, is to find preimages on hash functions. And the best example for this is Haraka 512, one of the permutations that we studied in our paper, because Haraka is a hash function that is directly built on top of a permutation. Actually, it only hashes inputs of 512 bits for this version. And the way it does it is simply it has a permutation which operates on 512 bits, and it XORs the output of the permutation to the input. And then it truncates to 256 bits. And then you have your hash. So of course, finding a preimage of this, for example, a preimage of 0, this is exactly a meet-in-the-middle problem. You want to find an input x such that truncation of x equals a truncation of p of x. More generally, this is going to happen when we have a compression function based on a block cipher, and if we fix the input, the key input, because on block cipher you have not only the input x but also an input key. If you fix that, you get a permutation. And so you could still apply the same techniques. Why do we care about quantum attacks? Well, in the case of Haraka, actually the hash function has been explicitly designed to be used in post-quantum digital signature schemes, such as strings plus. So we're going to care, of course, about its classical security, but at some point we have to ask the question of its quantum security. The classical generic preimage attack on Haraka 512 would be in time to the 256, because you can search exhaustively. And we already know since Eurocrypt 21 by a paper by et al. That there is an attack, because you can find a preimage using a meet-in-the-middle attack in less than that. But then you could still argue that, well, OK, there is a classical attack, but it could still be safe against a quantum adversary, because having a preimage attack in time here to the 240, does that mean that I have a quantum preimage attack better than the generic one? The generic one is actually quite good, because we have Grover's algorithm in the quantum setting, and this one is in time to the 128. So to have a quantum preimage attack, I need to do better than that. But actually, in our paper, we show that you can also do better than that in the quantum setting. So you have a preimage attack that runs better than Grover search for Haraka. Now, meet-in-the-middle attacks can become quite complicated. There are many techniques applicable. If you combine all of this, it can become quite difficult. But to search for these very complicated attacks, what we can do now, or try to do, is to use an automatic tool. Now, the idea is you're going to use some sort of modeling to model the space of possible meet-in-the-middle attacks and to search for the best one among them. And this was originally proposed at Eurocrypt 21 in the same paper, where the authors basically modeled the IES-like compression functions. I'm going to talk about this a bit later. The idea is simply that you have a description of all possible forward and backward paths, which define completely the attack. And now you try to find the best attack among all these possibilities. Now, in this paper, the possible backward and forward path, they were basically defined and constrained by a set of local rules. And I'm not going to go into these details because we use a very different approach. So modeling strategy is actually specific for permutations. So it's not going to include the key schedules, which was the case in the previous paper. But it actually allows to target a bit more than AES-like permutations, which is good. And also, the model that we get out of it is actually extremely simple, so that I can hope to present it during this presentation. And this modeling also includes quantum meet-in-the-middle attacks, hence the result on Haraka that I just talked about. And of course, there are many, like, it can be applied. We applied it on many primitives. You can select your best one out of the list, but I'm going to speak specifically about Haraka here. OK, So now I'm going to start by explaining how we abstract out permutation design, specifically a substitution permutation network. And this is going to be quite fast because the only thing we have to do here is basically throw away all the details we don't care about and keep only the structure, the abstract structure that we need to use. And then I'm going to explain how exactly the search is done on this meet-in-the-middle attack and how we model this into MILP. And finally, some examples on Harka 512. OK, so we start with permutation design. An SPN permutation, so a substitution permutation network, is like an SPN cipher without a key. So that's how it's usually it's represented with a state which is made of a certain number of cells. Let's say B cells of W bits, so that would make a state of W times P bits. And the round function operates with a nonlinear layer, which applies S boxes independently to all the cells, and a linear layer, which applies a linear function. Now, I'm going to focus on the example of present here. Actually, this is not present. It's a small present because it had to fit in the slide. But present is actually, it takes actually this linear layer, which is the permutation layer, very literally, because the linear layer only permutes the bits in the state. So initially, the state has 16 cells. Here, it's going to have 4 cells to fit in my slide. But this is the kind of design we're focusing on. So you have these S-box layers. And between the S-box layers, you just permute bits in the state. But this is nice because you have a very, like this is a graph, basically. And you have a very nice representation for this scheme. Unfortunately, Haraka is not based on present. It's based on AES. So here goes my nice representation, and here comes the AES. AES is basically I guess the most well-known block cipher out there. And this time it has a state which is represented as a matrix of bytes. So the S boxes operate on the bytes. And the linear layer, it does 2 things. First, it permutes the bytes. That's a shift close operation. And then it mixes, so it applies a linear function on the columns of the matrix. Now, this has nothing to do with my previous drawing, but actually it does. If I use the following technique, the super S box, which basically consists in putting together the S box layer and the mixed columns of the previous round, now I obtain basically a big S box that operates on columns, on 32 bits. And between these layers of super S boxes, the only thing that remains is the shift rows, the permutation of the bytes. So now I have a layer of super S boxes, followed by a permutation of bytes, followed by a layer of super S boxes, etc. So in our paper, basically started from the present representation of these permutations. And actually, we could then include AES by basically, using the same representation. So this is why I can focus on these nice graphs, weighted graphs. OK, so now we get to the abstract representation of this SPN permutation. First of all, if there are round constants, there are round constants usually. We just remove them. We don't care about that. The S boxes, of course, they're still here. They could be arbitrary functions. We also don't really care. And we're going to just, instead of writing the round function, we're just going to replace each S box by this cell here. And we're going to say that each cell is basically a small list which corresponds to the possible values that this S box can take. So here, this is an S box of 4 bits. That's basically 4-bit input and 4-bit output. So there are 2 to the 4 possible values here in this set, this small list. So now we have all these cells in our graph, and they are connected by linear relations. The goal, the thing we're trying to solve, is basically to find an assignment of values to all these cells that satisfies all the linear relations in them. And now I have removed practically everything, and I just have a graph that remains. And this is what I input to my code, which is going to find the attack. So now let's find the attack. we're going to define the following. So this is just a fancy way of saying what I said at the beginning of this talk, actually. The meet in the middle technique is just computing something forwards, computing something backwards, and then trying to merge, to match between the two. So we're going to define this, I think we call it a reduced list. It's if you take a set of cells in the graph, there are some relations between them, and you want to find all the assignments to these cells that satisfy other relations. Now, the meet in the middle characteristic, the whole attack, is defined only by 3 sets of cells, and actually only 2. The one that defines the forward computational path, the one that defines the backward path, and then the union of the 2. There is also a small constraint here, because for the attack to actually work, the union of the 2 has to cover around in the middle. That's just technical. Okay. And what the attack does is simply compute the forward path, all the possibilities for it, compute the backward path, all the possibilities for it, and then try to match the path. So compute all the possibilities when you take into account the relations between the forward and backward cells. And now I need to convince you that for any choice of this forward and backward cells, there exists indeed an algorithm that does this, and that has a time complexity that we can compute. And this is going to be quite simple. Let's have a look at a forward list. Again, on my representation of a small present-like permutation, the forward list is going to be computed forwards. And what we do is simply the following. I arrive here at round 0, and I need to take a value for this cell. There are 4 bits here that I don't know because I'm only starting. So I take 4 bits. I guess 4 bits. Now I have value for this cell. And then I can pass 2 bits to the next cells because there are linear relations here. So that's good. I already know 2 bits for the next round. But I need to, I'm missing here 3 plus 3 bits. So I take values for them. And I continue like this round by round. And then at the end, what did I do? I obtained basically only by guessing bits, I obtained a valid assignment, a valid choice for the forward path. And you can see that the total number of such valid assignments is exactly the sum of the weights, so number of bits of the cells, minus the sum of the edges that there are in the graph. In that case, it will be 12. So I need to guess 12 bits to obtain the value. That's the forward path. Now for the backward path, I just took the same slides and I changed the colors because we can do exactly the same thing, but in the other direction. Now we go back. If we want to find all valid assignments for these 4 cells here, taking into account the relations, we just start from the last one, and then we go backwards round by round, each time guessing what we need. And of course, in the end, we can obtain like this all the possibilities for the backward path. Now we arrive at the interesting moment, the final step in the attack is to compute all the pairs of backward and forward path which are going to match. Because you see this backward and this forward list here, they are seeing each other. There are linear relations between them, which are supposed to be satisfied. So if I put them together here, in this example, I have 12 bits of linear relations between them. Unfortunately, it is possible to compute efficiently the list of pairs of these backward and forward values, satisfying the new linear relations. That's merging the 2 lists. And the list of assignments, the merge list here, is equal to the size of the forward times size of backwards divided by the amount of linear relations that we match. So we have an algorithm for the 3, that completes the meet in the middle attack, because now we can really, for each choice, we just recompute everything and check the rest. So we have an algorithm, and this algorithm depends only on the sizes of the lists. And the sizes of the lists depend only on the choices of cells. So we have immediately, for any choice of cells, even a bad one, we have an attack with a classical time complexity, which is going to be given by this assuming that you first compute the forward list and that afterwards you basically go through all the possibilities for the backward path. That's a bit of technical point. And in that case, you need to store the forward list. So you have an algorithm with these complexities. That's a classical attack. For the quantum attack, well, you also have a quantum algorithm. I'm not going to go into the details, but basically, the quantum algorithm, it looks like what the classical one, except that in the step when you go through the choices for the backward and merged, you can do that with Grover search. And so you get this nice square root time speedup associated to Grover search with some more technical details. And the quantum memory is also this storage of a list. But what matters here is that I have formulas that depend only on the choices of backwards and forwards. So I have a search space. All the variables for the backwards, I put Boolean variables for backward and forwards. And from them, I can deduce the sizes of the lists using only linear inequalities. And this is a modeling, like this is a mixed integer linear programming, basically. And from them, I can deduce my objective function, which is the complexity of the attack. There are some technical details, but I'm just quickly throwing them here. I presented a very simple version. Actually, to get really nice attacks, you need to reduce the memory used as much as possible. And this is done by creating some guesses inside the path. And they will naturally appear. This is basically pre-compute. You can basically pre-compute some matchings between the backward and forward path. Something which is also very important for AES and also for Haraka is that in the AES case, this box that you see here, it's actually a mixed columns. There is a mixed columns in there, which is a linear operation. So actually, the matching can traverse a box, even if you don't know the value of this precise cell, you can go through it. That's really important, but again, I'm not going to detail that. Okay, let's see what this gives for Haraka 512. So Haraka 512, as I said, is already broken from Eurocrypt 21. Actually, this attack is an attack on an extended version of it, and it runs in time to the 214. In our paper, what we showed that we didn't reduce the time complexity of this attack, but we showed that you could reduce the memory complexity from 2 to the 128 to the 16. This is actually quite nice when we go to the quantum setting. Because if I give you a classical attack, which has a time 2 to the, which has this time here, and a memory 2 to the 128, even if you apply Grover search as much as you can, Grover search is not going to reduce. It can reduce your time complexity sometimes, but it doesn't reduce your memory complexity. So with this, you couldn't hope to obtain an attack doing better than the quantum generic one. But with the path that we obtain here, we can basically put a square root complexity on the time, and we don't have this problem anymore. And there, of course, it's not exactly a square root, and there is some factor that goes in there, but it's basically what happens. I just wanted to talk a bit more of an attack on 5 rounds exactly, so just a full version, which is classical and in time to the 224. By the way, this is how it looks like. It's kind of a mess, right? So that's a representation of Haraka as my present-like as a present-like permutation, and basically each of these boxes here is a column. It's a big permutation. It's actually 4 AES states. So you have like 16 columns. And of course, there is then an exchange of the bias, which is a bit messy, and it doesn't print very nicely. But what matters here is that, well, the path is extremely complicated, and I can assure you that I wouldn't have found it by hand. It's kind of the point of using automatic tools to find this kind of thing. This attack on 5 rounds runs in time to the 224. I just wanted to mention that 224 is quite large, right, as a complexity. But actually, the attack is kind of practical in a certain sense, because what you can observe is that actually it has a very small memory, and it comes from the fact that this full pre-image attack is actually a partial pre-image attack that will repeat many times. So instead of going for the full pre-image, what you can try to do is to go for a partial pre-image. And this one is going to become practical. You can really observe it by hand. So so what I did here is just compute something to get 64-bit partial pre-images. So instead of having a full 0, I only have 64 bits to 0. And the attack runs in about time to the 32 and memory to the 32 as well. So it can run on my laptop, not exactly taking a weekend, a bit less than that. But yeah, this is a bit better than doing to the 64 computations. All right, so just to conclude, I wanted to stress the fact that modeling this meet-in-the-middle attacks, it gets really simple when we face permutations. And also that these attacks actually perform quite well in the quantum setting. We got up to a quadratic speedup on some of these. However, of course, this approach is really tailored for permutations. If you have other degrees of freedom that come from a key schedule, it's much more difficult, and it's an important and interesting open question. So you can find the full version of the paper on ePrint and the code on GitHub. And thank you for your attention.
Thank you, Andre. Are there any questions in the room or in Zoom? I have when do you think it would be possible to adapt the tool to take into account by clicks, for instance, or sieve in the middle for the matching? Have you had a look at that?
So by clicks, I don't really know. The sieve in the middle, so far I'm getting the impression that it can be somehow handled. I'm working on this at the moment. So basically, the sieve in the middle is something where you're attacking so you're doing a key recovery attack, right? You're attacking present, and you're remarking that if you know multiple edges here and multiple edges here, like 2 here and 3 here, you can have some matching also in the middle. I think this is more or less at least partially covered by making some kind of guesses. So like by but some kind of guess and determine technique, which is partially covered by this framework. But I must say that this is ongoing work.
Thanks. Are there any more questions? Okay, then if there are no more questions, let's thank Andre again. Thank you very much. Okay, thanks. So the next talk is construction and the constructing intentional weaknesses in symmetric ciphers. And the talk is given by Gregor Leander.
So this is joint work with Christoph, Tim, and Patrick. So as an introduction, we think that backdoors or intentional weaknesses, which is, I think, overlapping objects, an interesting research problem and an interesting topic in many dimensions. Yeah, so it's politically interesting. It's interesting because we saw these things being deployed, and our main point is it's also interesting for, from an academic view. And maybe one important disclaimer. So we think it's bad. Yeah. So and I hope it's clear without saying this, but I thought I better make it clear. So our main point is not to advertise for deploying backdoors, but understand and then prevent it. So there are many different flavors of vectors, and they have different, you can have very different properties. And I'm not going to define this precisely in the talk, but just give you an idea what I mean. So the main properties that we were interested in is undetectability, which means you will not find the vector. No? Otherwise, it's not a good vector. Untraceability means that if somebody uses the vector, you're not able to tell. So that's more the case if you think, for example, of a tweakable block cipher, and maybe there's a special tweak which makes the cipher weak. Yeah? Then even if somebody uses this special tweak, you shouldn't be able to tell that this was the special tweak which made the vector, which activated the vector. And it should be practical, meaning that if you use the vector, then you're able to practically break the scheme. No? Otherwise, it's not worth. And if you actually achieve all these properties, then you basically get a public key. No? And we don't. So we aim at less. But it's an interesting approach to public key, I think. Okay, yeah, and what we are not achieving, maybe I should say, we are not achieving this untraceability. So our vectors, once used, are kind of revealed. And we have two, in the paper is twofold, two contributions. One is deconstructing, and there we look at the GA1 algorithm. I'll briefly recall what this is and explain how this vector or maybe more intentional weakness was built, what we think has been built. And we are going to explain ways following the malicious framework, how you can actually build nice, what I think is nice and natural looking block ciphers, tweakable block ciphers with vectors. Okay, I'll start with the constructive part, namely how to build tweakable block ciphers with the vector. Yeah? And this is, we build up on work on this malicious framework from Crypto 2020. And there the idea is that it's a tweakable block cipher, and without giving any details, there are tweaks, a pair of tweaks, two specific tweaks, and if you use them, then you will find the probability 1 differential. And then you can use this to recover the key. So this is the idea. And it's good in the way that the way they do it, because they hash the tweaks, it's undetectable. So you will not be able to find the vector, and it's practical, leading to practical attacks. It has also some downsides, and this is why we think it's worth looking into it again. Namely, it's very non-natural. Yeah? So they start with these tweaks and basically have to modify the round function, the linear layer of this round function, in order to be able to make sure that this differential is probability 1. So they have to basically choose a random linear layer for their round function, for the linear layer of the cipher. And this means you look into low MC ciphers, which is a cipher which has its corner to exist, but it's not the natural general purpose block cipher. No? Okay, and our idea is basically to do the same thing, but not build a probability 1 differential attack, but try to build the weakness on invariance instead of differentials. Okay. And here is what we do. We have two examples. One is based on AES, and I'm only going to explain this one. And then we have another one which is more involved. And I think it's interesting. If you're interested, you should have a look at the back. So there's one AES, thanks to Andre, I don't have to explain. And I hope anyway, I guess if you don't know how AES works, then you're maybe in the wrong session. So there's an invariant space. Namely, if you take an AES space and you put the first and the third column to the same value, and the second and the fourth columns have the same value, then this is not going to change through the round function. Yeah? So if you apply sub bytes, this is clearly not going to change. If you apply sub rows and you carefully check, it's not going to change. And for mixed column, it's not going to change, because if you input the same columns, you're going to output the same columns. Okay. And so why is this not breaking AES? It's not breaking AES because if you add a key, then automatically this is going to be destroyed with super high probability. Yeah? For one round, it's very unlikely, and for more rounds, it's just not going to happen. Okay, so this is why AES is not. Now we wanted to have a weak cipher, so it's very easy to get it weak. We just modify the key scheduling. Yeah, so the first change we do is we modify the key scheduling, and so you take a key scheduling, and I'm not going to explain you what exactly we do, but the main point is you only output symmetric keys. So you have a key, so each round key is only 64 bits, but it doesn't matter. If you have enough rounds, it's not a big issue. So also the round keys are like the first column equals the third column, and the second column is equal to the fourth column. Yeah, and with this, you now get an invariance and weakness which works for any number of rounds. So the cipher is weak. I'm not going to explain you how to use this, turn this into key recovery, but you can do. Yeah. So you get the weak cipher. Okay, but now the problem is we have a weak cipher that is weak always. So we have to make sure that it's weak only for the tweak, the backdoor that we want to embed. So the second thing is we add the tweak. And so there's one thing, so you take a tweak, T0, you fix it, you randomly choose it, and then you hash it. And this hashing is basically the idea in malicious framework, how to make sure that you cannot find the backdoor. Yeah, you hash it, and then you get as an output a string which is just long enough. Yeah? So imagine this is long enough, and then long enough meaning that we take for each round we take 64 bits, yeah, 2 columns of this hash as the round tweak. Okay, and for the rest of the remaining columns of the round tweak is just 0 all the time. And then given this tweak, we're going to choose the constants. Yeah? So there will be round constants, like in any good cipher, there should be round constants. And we choose the round constant so that the sum of the tweak and the round constants are symmetric again. Okay. So what happens is you start with this symmetric state, you apply all these round functions, you get the symmetric state, you add the symmetric key, you get the symmetric state, and now comes the tweak. So you take this tweak, you hash it, and because the tweak is T0, this thing is symmetric, and you get a cipher which is symmetric, so it can be broken practical for the tweak. Sorry, for the tweak T0. And now what happens if you take a different tweak? If you have a different tweak, then this is going to not fit to the round constants. Just get basically because of the hashing, you get the random values here, and so the probability that this one is symmetric again is super small, and so you get something which is not secure, which is not weak, except if you input T0 and nobody knows T0, so that achieves what we want. So it's undetectable. Nobody will be able to find this T0, and it's practical. Well, I don't exactly explain how it's practical, but you see that the weakness is strong. Okay. So this maybe is not super surprising. We have, yeah, as I said, we have something called boomslang. I'm not even sure I pronounce this correctly. Tim's coined it like this. So this, I think, is so the AES variant. Everybody will be able to tell. So this is folklore thing, well-known weakness. But this one uses a nonlinear invariant over 2 consecutive rounds, and it's hard to detect. Hard to detect in the sense that we don't have automatic tools to find these weaknesses. Yeah, maybe we could build, but for now, I mean, it's really hard to detect. So yeah, so this shows that there are non-trivial versions to the same thing. Okay. So that was for the first part. And now let me come to the GA1, the deconstructing weaknesses. So GA1 is this. No, actually, it's not this because it's for old phones. Yeah, so it's was used in former versions of GPS, yeah, for the data encryption of mobile phones. Okay, and it is actually a stream cipher, which takes a 64-bit key and has a 96-bit internal state. And this was not public, but at some point last year at Eurocrypt, it was published, and there was a weakness. I mean, it was broken. And how was it broken? It's broken because if after the initialization phase, the joint state of this register A and C, which together has 64 bits, so it could have, after initialization, it should have all close to all possible 2 to the 64 possibilities. If you run to the all possible 2 to the 64 keys, but it doesn't. You only get 2 to the 40. So and then the attack is super easy. You guess these 2 to the 40, and you compute this and check if it's. So this is easy, and actually it's not so hard. I mean, if you to find this vector, I don't know. It's always like with cryptanalysis. If you have the right idea, it's easy. So here it's only finding this vector is linear algebra. You have to compute the kernel of this mapping. It's not like you have to run to this 2 to the 64 to see this, because it's all linear algebra. Computing the kernel of a matrix is enough to see this attack. Okay. So then the next question is, how did they do it? How was this constructed? Is it easy to find these LFSRs? So is it maybe an intentional weakness, or it's just unlucky? No. And so what the paper last Eurocrypt did is to check how likely this is to happen. And then you can have such a graph. So you take, I think, 1 million LFSRs, pairs of LFSRs of the right dimension, and check what is the dimension of the image of the space, or what is the dimension of the kernel. So this is the kernel, because if you want this small image, you want the large kernel. So here I have on the x-axis the dimension of the kernel, and for GA1 this is 24. And in this 1 million tries, the highest kernel that was observed was dimension 9. And if you extrapolate a bit and make a reasonable assumption about what is the probability, then the probability or the effort to find such a configuration is 2 to the 40 or 2 to the 50. So that's 2 to the 50 times trying LFSRs, computing linear algebra, and this in the early 90s is not possible. This is not how they did it. And so there's two things. There must be a way to construct this, and the second thing is this was not unlucky. So this was on purpose. Okay, and this is 2 points. The question I want to answer is, how was this constructed? So we don't know, right? Basically, we have one way to construct this, but if this is the way they did it, who knows? Okay. So we have to look at the initialization, because this is the thing that makes it weak. So this is register A and this is register C, and this is what happens. Initialization works by feeding in the bits of the key. So that's how you do it. That's how everybody would do it. So you feed in the key, and then you clock the register. You feed in the next bit of the key, and you clock it, and so on. And for the second register, you actually start with a different bit, but basically you do the same. You feed in the key. And so what you want that the image of this linear mapping the 64-bit key to these two states, the image is small, so you want a large kernel. You want many keys to be mapped to 0 in both LFSRs. 0 state here and 0 state here. Okay, and just to have some notation, you will have this feedback or the characteristic polynomials of this LFSR. If this is denoted by G, then the linear mapping describing the initialization key goes to initial state. I denote it by MG. Okay, so what I want is I have to look at this linear mapping the key S to this state in register A and to this state in register C. And I want this to be 0 often. Okay. So there's one interesting detail I already said. So you start with a different key in register C, a different bit in register C. So it's just shifted. And I'll explain why this makes a big difference. Okay, first of all, we have to rewrite everything in polynomials. So if you know a bit about LFSR, that's not super surprising. So what we do, you write down this 64-bit key as a degree 60, a polynomial of degree at most 63, by basically just putting the coefficients as the key bits. So there's some tiny mistake, and not mistake, but I'm simplifying here a bit. And then the interesting why is it a good idea to rewrite it like this? Because a key being mapped to 0 is then equivalent to this polynomial, being the key-dependent polynomial. The key representation, the polynomial representation of the key is divisible by the characteristic polynomial. Why is this? Intuitively, the intuition is that this initialization is nothing else than computing this polynomial modulo G. Now you flip a bit, and depending on if they set or not, you're going to add the polynomial g. So that I think it makes sense that this is like this. Yeah, so it's just reducing mod g, and so if this is reducing mod g, then it's 0 if and only if it's divisible by g. Okay. So now we want we're looking at the variant without shifting. Yeah? So that's maybe the more natural variant which we would design. So you have register A without shifting and register C without shifting. So now you want, so this link I just explained, and what you want is you want to count the number of keys which are mapped to 0 in register A and mapped to 0 in register C. Yeah? And with this link, so it has to be 0 in both. With the link, that means that this polynomial P of S is divisible by both the feedback polynomial of LFSR A and the feedback polynomial of the second register. Yeah? And now, because those are primitive and different degree, if they both divided, the product is to divide it. Yeah? But the product now is a degree 64 polynomial. Yeah? And this has to divide a polynomial of degree 63 at most. So that's not going to work. So that's only going to work if this polynomial is 0. So what does it mean? If you don't have shiftings, then the only key which is mapped to 0 in both states is the 0 key. So that is, makes a good cipher, because it tells you that if you do this initialization, you get no entropy loss. Yeah, so this is a nice construction. So, but they didn't do it like this. Yeah? So there's the shift. And why is the shift? What is the effect of the shift in this polynomial setup? So yeah, I show the shift again. So what happens is you can think of shifting as the polynomial being multiplied by x to the 32 and then reduced modulo x to the 64 plus 1, and just wrap it up. And this is the wrapping. And now what you want again, you want it to be 0 in the first polynomial, and you want the shifted key to be 0 in the second LFSR. And now you do again the same conversion with the link I explained to the polynomials. So now this means that the first polynomial has to divide this P of S, and the second polynomial has to divide this rotated polynomial. And now there's no obvious link, because with respect to factorization, this polynomial and this polynomial, they behave independent. They are not independent, but of course, heuristically and also experimentally, they behave very independent. Yeah, so the divisibility of this one and the divisibility of this one is two different things, and so there's no contradiction anymore. So it's possible. Yeah? And yeah, it's a nice small change that makes this attack possible, this weakness possible. Okay, so that's important, but it still doesn't explain how you find those now. Yeah? So how do we find? We still have to find this GA and GC. Now we know how to write this in polynomials, and so far I didn't explain how to find it. So the idea is you turn the problem around. Yeah? Instead of trying to find these polynomials, starting with polynomials, and trying to factorize, trying to see if they have a good polynomial, you're starting with a kernel element and try to find the corresponding polynomials, the feedback polynomials. Yeah, so given P of S, we try to construct GA and GB so that this given key is mapped to 0. And that's easy. So what you do is you take this polynomial PS and this other polynomial and just factorize it. And you hope that it has a irreducible, a primitive factor of the right size. And why is this a good idea to do it like this? Because primitive polynomials are not rare. So if you pick a random polynomial, so then its primitive is not very unlikely. Okay, you can write down a formula. This multiplication here already assumes that things behave independently, and but it works. Yeah, I mean we did experiments and was after like roughly 1,000 tries, you're done. You find this setup that you wanted. Okay. So now I explained you how you can rewrite everything as polynomials, and how given how you can efficiently find polynomials so that at least you have one element in the kernel, namely the one you started with. But still, we don't want a kernel of dimension 1, which is now clear. We want a kernel of dimension 24, in the case of GA1. And how do you do this? You choose PS special. And basically, you make sure that, yeah, okay, you look in the paper if you want to know how to do this. So there's a special choice of P, so that if this P is in the kernel, then you know many elements in the kernel. Rotated variants in principle of this P are also in the kernel. Okay. So and this works. Yeah. So we implemented it, super efficient. So it also was already efficient in the 90s. You can check if the kernel, the actual kernel of GA1 is of this form, and it is of this form. It's interestingly that you could weaken it below 40 bits. Yeah. So now the security is 40 bits, but you could also do with the same setup achieve even weaker systems, but they didn't do it. Yeah. So and this 40 bits is something which more or less officially was export control in the EU. Yeah. So that makes sense that it's 40 bits. Okay, and all these details are in the paper, and kind of the correct version of all what I said is in the paper without the simplifications. And that's all I wanted to say. Thank you very much.
Thanks, Gregor. Are there any questions in the room or in Zoom? No questions? Okay, thanks a lot. Thanks again, Gregor. So the last talk of this session is Simon's algorithm and symmetric crypto generalizations and automatized applications. And the talk is given by Lucas Ten.
Yeah. Hello, everyone. Thanks for the introduction. I just want to add the paper is joint work with Federico Canale and Gregor Leander. And well, the paper is titled Simon's Algorithm and Symmetric Crypto. So I want to start by explaining what Simon's algorithm is. And Simon's algorithm is a quantum algorithm that solves a rather specific problem, namely Simon's problem. And for Simon's problem, you are given a function f that maps n bits to n bits. And you are promised that the function is such that there is a secret period s, and that means that f of x is equal to f of x XOR s for all x. Yeah. And now the goal is to find the period s. And in a classical world, you can show that you will need at least roughly 2 to the n over 2 queries to f. So that's essentially the birthday problem, because you have to find a collision in it. But in the quantum world, there's Simon's algorithm. And with Simon's algorithm, you only need big O of n quantum queries, and then some basic linear algebra to recover S. And yeah, I mean, that's nice. It's an exponential speed up. But why do we care about this? We as like people who are doing symmetric cryptanalysis. And the reason why we should care was essentially given by Cuvacaro and Mori first in 2010, where they gave a quantum attack based on Simon's algorithm against Swion Feistel. And then in 2012, they gave one against the Evan-Mansour construction. And this I want to present here. So for Evan-Mansour, I mean, it's a construction to construct a block cipher, and we need two secret keys, K0 and K1, and one public permutation. So everyone knows this permutation. And what we do is we simply add K0 to the input, then apply our permutation at the other key, and that's what we need to do to compute the encryption of X. And in a classical world, you can prove that this is a secure block cipher. But in the quantum world, when we consider this function, f of x, which is simply the encryption of x or the public permutation p, then we will notice that when we write this out, then that we have this P of X XOR K0 and then XOR P of X. So this means that if we add K0 to the input, then this will be cancelled out, but K0 will appear here. And that means that the output value will not change, right? Because it's the same as before, just swapped around. So as I just said, then if we have a function of this form, we can use Simon's algorithm Simon's quantum algorithm to find K0 with just a polynomial amount of queries to the encryption. And once we have K0, finding K1 is easy, and therefore the quantum version of the Evan-Mansour construction is poor. Okay, so that was the motivation for our work. And now we have two contributions, and the first is an automize or an automatic way to find new applications. That means essentially to find these periodic functions for other constructions. And then our second contribution is a negative result on potential generalizations of Simon's algorithm. Okay, so let's start with the automized applications. And I mean, like I just said, once we have a periodic function, you can just use Simon's algorithm to recover the period, and then maybe the period is like just depends on the secrets and can be then used for a distinguisher, or maybe the period is the secret key or something. Then we can also build key recovery attacks. And the important point is that these attacks will be fast in the sense that we will only need a polynomial amount of quantum queries, in contrast to, let's say, Grover's algorithm, where we still need an exponential amount of queries. So, I mean, for the Evan-Mansour construction, finding this function is quite easy because the construction itself is rather easy. But if you study more complex construction, it becomes really cumbersome, and you don't want to do it by hand anymore. And so we want to automate it. We want a computer to do this for us. But the question is, how can we do this? And our approach is quite simple, actually. We will just enumerate all sensible functions. And of course, the devil is in the detail. What does sensible mean? For us, sensible means that the periodic function somewhat depends on the construction. Yeah. So, I mean, for example, for the Evan-Mansour construction, we use this internal permutation P and maybe the encryption itself, and then XOR, that's it. And then once we have such a function, we will instantiate it with a small block size, say, for example, 4 bits or something. And then like checking if there's a period is easy, because we can just evaluate the function on all the inputs and then use a trivial brute force approach to see whether there's a period. And once again, the periodic function for the Evan-Mansour construction, or the attack on the Evan-Mansour construction, looks like this. And to represent such functions, we are going to use circuits. So the circuit for this function would look like this. So here we have an input, and then we apply the permutation and the encryption, and then we XOR this together. Okay, so let's go into a little bit details there for circuits. So this is actually the circuit, or the circuit representing the function that was used in the attack on the Feistel cipher in 2010, which is actually in contrast to the one on Evan-Mansour, just a distinguisher. And so I want to use this as an example for what we understand as circuits. So, I mean, most importantly, the circuit is essentially just a graph, yeah. So a directed acyclic graph, and a subset of the nodes is, I mean, are the input. So this is this capital X, and notice that we here have like the small x is just the input of the function, but we can also have like constant in our input set. So here the alpha, there's an alpha 0 and an alpha 1 in the attack, which are constants. And then there's an additional input bit B, which essentially switches the values of these alphas. Okay, and then other than that, for the non-input nodes, the non-input nodes are labeled with gate functions. So here EL is the left part of the Feistel cipher, so the output of the Feistel, and this is just XOR as usual. And then for the XOR, the order of inputs, of course, does not matter, but for the encryption, course, it doesn't matter which one is the left and the right or the first and second input. And so we are also going to label the edges to make clear what the order of inputs is. And last but not least, we need some node. This is actually the value, the output value of the function. And for convenience, this will just always be the node all down below. Okay, so then let's consider some examples, some rather abstract example of a circuit. And notice here, there is a node that is not really used anymore. And I think intuitively, it should be super clear that it makes no sense to consider such a circuit, because, I mean, if we consider the same circuit without this node, would compute the same function, right? And then there are two other nodes. Both are labeled with G0, so they both compute the same function. And they also have both the same inputs. So again, it makes not really sense to do this like this. So we don't want to do this. And essentially, we say that such circuits are then in a non-normal form, and we only want to consider circuits that are normal. So an example of an equivalent circuit that computes the same function would be this. And thereby, we can reduce the number of circuits that we actually have to consider, and therefore, I mean, reduce the runtime of our search by quite a lot. And this is not enough yet. So we need even more restrictions. And to do so, I mean, we just say that we want to define some rules, and the rule just takes a circuit as input and then outputs 0 or 1, depending on whether the circuit is useful or not. And just some example for such rules. So these rules are more concrete, yeah. So not on abstract circuits, but when we, for example, know that one of the gate functions is XOR, which will always be the case, then again, it makes no sense to consider circuits that compute something like A XOR A, because, I mean, not only for the output, but also in an intermediate step, because when we want to have a 0 or a constant 0, then we can just add it as a constant to the input nodes. And also, we could restrict the number of queries that are actually allowed. So we could say that the function that, I mean, the function we are looking for should only query the construction that we are trying to attack, like only once or only twice, something but like this. And of course, we can then also say that the query to a construction should depend on a non-constant input. And to do so, I mean, this would just be like a reachability test on the underlying graph. And you could go on, like, essentially you can do whatever you want. It only has to be efficient. And I think this is also clear, right? If you say that the rule is that the circuit that you have in the end has like a period or something, or should be that what you want to search for, of course, you could define this in theory, but it makes no sense in practice. And the key point here is that these rules are not only checked before we do our period test, but on all intermediate steps, so that we can, I mean, if you think about the whole thing as a search tree, then we try to, to cut as soon as possible, like when we go down from the root and the leaves are the circuits that we actually will test for periods, we try to cut large parts out of the circuit. And to give you some numbers, here is the search for 415, so another attack that was already known before. So we first try to rediscover known attacks to see whether our approach would actually work. And this solid line is the number of circuits you would have to test if you do the like trivial approach, where you don't do any of these tests or normalization or anything like this. And notice that this scale is logarithmic. So here is already 2 to the 40. So to take circuits with 6 non-input nodes, you would need to check 2 to the 43 circuits. So that's would take a bit longer than a weekend on my laptop, at least. But what we can do now is, so if we do this and we define our rules, then you only need to do like 2 to the 23 rules. And I mean, these rules are easily to check. And so in the end, we only have to test about 2 to the 14 or 16. No, wait, it's over. Yeah? Not so important. But what matters is that we can then do all these checks in only a couple of minutes. Okay, so let's talk about a specific example. So one of our new attacks is on the foreground MISTY RFK construction. So MISTY is here. It's kind of similar to Feisel, but the round function is not applied here in the middle branch, but on the side. And this RFK means that we consider, I mean, the round function is not a new random function in every round, but one fixed function, and then we add a round key after we apply the round function. And so the setup of our search for this was that we just had one input node, which, I mean, just the input of the function. And then as gate functions, we had XOR and then the left part of the encryption and the right part of the encryption and the round function and also the inverse of the round function. So in contrast to Feisel, we know that the round function actually is invertible. And then as rules, of course, we use this normality so that there are no nodes that aren't used anymore, or there are also no nodes that compute essentially the same. And then again, also the XORs should be same. Yeah, I already said that we don't want to do like A XOR A. Also something like A XOR B XOR A also makes no sense. And then since we have this F and F inverse, this could also cancel out. We also don't want to do something like this. And one technicality, I mean, all our gates will take 2 inputs, but of course F only takes 1 input. But in our implementation, it actually has to take 2 inputs, but then we just enforce that these inputs are the same. So in the end, it's just 1 input. Okay, and so again, here the trivial approach would have been to test 2 to the 25 circuits, but with our approach, we only need to check 2 to the 18 rules, and then the number of circuits that, let's say, survive, that have to be checked for periods is only 2 to the 12. And what our search then finds is this circuit. So we take the input, we apply the round function, we add the input again, and this is then the second, so the right input of one encryption query, and the left input is just the input of the function. Then we add the outputs, so the left and the right output, and we then see, or we then can show, I mean, our implementation then tells you that this has a period, and then it's easy to see or easy to verify that the period is actually K0. And that means that using Simon's quantum algorithm, we then can recover K0 with just a polynomial amount of quantum queries to the MISTY RFK construction. And therefore, this is also then totally wrong in the quantum setting. So we have some more attacks. All these constructions that we studied, or that I give here, were actually already studied before, but only distinguishers were found. And these were actually similar to the distinguishing attack by Covacado and Mori against the Fourier Feisel, so with like constants as input that switch based on one input bit. And in contrast to that, we give key recovery attacks. So on 4-round MISTY RFK, that's the one I just showed. Also on 5-round MISTY LFK, and on 4 and 5-round Feisel FK with a small thing for the 5-round there. The round function must be a permutation, so invertible, which strictly speaking must not be the case for Feisel functions. And one thing about these distinguishers, of course, one could use them to build key recoveries based on, for example, the Grover meets Simon approach. But then again, the number of queries one needs is not polynomial anymore, but exponential. And since we only rely on Simon's algorithm, we only need a polynomial amount of queries to it. Okay, then let me quickly talk about the generalization part, so about our negative result. Okay, so let's first consider Fourier transform of a Boolean function f, which is just the sum over all y of -1 to the inner product of x and y plus the function evaluated at y. And we can rewrite this as the matrix product of H0, so the standard Hadamard matrix, which is, just the entry at xy is -1 to the inner product of x and y. And well, we multiply this with the vector where we just take the function value to negative, or we take -1 to the value of the function at this point. And now, if we don't really study Simon's algorithm, but the Bernstein-Vasirani circuit, which is rather close to Simon, so it's not a big deal. But there, essentially, the circuit in the quantum attack yields a vector from the span of all the points that lead to a non-zero Fourier coefficient. And now, if we consider a function that is essentially as in Simon's promise, so there is a unique period S, then we would have that this vector is such that the inner product with the secret period is 0. So this is where this comes from, why this is close to Simon. And now our generalization is that we look at like a slightly different transform where we don't use the standard Hadamard matrix anymore, but just any Hadamard matrix. So just a quick reminder, Hadamard means that the transform of the matrix times the matrix is the identity. And of course, the entries are -1 to some function g on base that takes as input the entry. And now the question is what meaningful properties of f we could catch with some or such a non-standard Hadamard matrix. And especially we are interested in whether we could find out something about linear invariant properties, because in symmetric cryptanalysis, all the properties that are interesting, or most of them like linearity, differential uniformity, and the algebraic degree, are all linear invariant. And this means that for any invertible matrix A, F satisfies this property if and only if F after A does. And now our main theorem here is that if for any A, there exists a B, so both invertible matrices, such that for all F, we have that this transform regarding H of F after A is the same as the transform of F after B, then H is equivalent to H0. And this means that if H is not equivalent to H0, then we cannot catch linear invariant properties. And therefore, we believe that the standard Hadamard matrix is the way to go if you want to study or if you want to use this for symmetric cryptanalysis. Okay, so let me quickly recap the talk. So we have had two contributions. First, the automatized applications, and there we developed a way to automatically search for quantum attacks based on Simon's algorithm, which only take a polynomial amount of quantum queries, and we use this to actually find new attacks against the MISTY and the Feisel construction. And for the generalization part, we studied generalizations of Simon's algorithm and also the Fourier transform thereby. And there we concluded that the standard Hadamard matrix is the best choice if you want to study symmetric or properties that are relevant for symmetric cryptanalysis. And so if you're interested in our work, the full version is available on ePrint, and a Sage implementation of our code to search for the periods is available on GitHub. And if you have any further questions or want to contact us, then these are our mail address. And that's it from my side, and thank you.
So are there any questions for Luca? Yes, please go to the mic, please, John. And my computer died, so if there are any questions in Zoom, please could someone let us know.
Okay,
So-
I was just going to ask, have you looked at any of the hashing, like the compression function kind of structures, the things where you have the block cipher and then you're using the key and feeding forward or something like that?
We looked also, for example, at hash counter and something like this. There were also, again, attacks already known, which we could also rediscover. And I guess we also, I mean, we can also use essentially the same idea to search for attacks based on the Grover meets Simon approach. And there we also find some attacks, I guess, on the permutation-based EDM construction and something else I think I just forgot. But yeah, so we looked at some constructions, but I'm not sure whether these are actually the ones you are talking about. But
Thank you.
Yeah.
Thank you. I have a question, Lucas. Have you had a look, or do you think it could be adapted, your tool? In some cases, we do an exhaustive search of like a part of the key and then try to find if it applies Simon in the state, so combining Grover and Simon. Do you think you could detect this kind of attacks by adapting the tool?
Yeah, like I just said, we can, I mean, essentially use the same tool and like add another node, which is then essentially the part where we would apply Grover to do this. And yeah, you could do this, but this of course then increases the runtime. So
Okay, thanks. Are there any more questions? Okay, if there are no more questions, then we'll thank again Lucas and all the speakers of this session. Thank you. So I think there's a break until 4:30 now, right?